Let me make sure my volume's up, and it wasn't. Good thing I did. Okay, so here we go. So what I want you guys to think about today is timeless equation. What the heck is that? Well, we're going to find out today. But basically, every equation I've given you up to this point, it's all about time. Everything has to do with time. And really, we only have two equations. I'm going to go ahead and put them on the board. Okay? So up to this point, the only equations we really have are x final, and sometimes we call it x of t, but I'm just going to call it final for right now. Okay? A little easier to look at. You're going to see it a couple of different ways, so it doesn't hurt to see it a couple of different ways now. X final is equal to x initial plus velocity initial times time plus 1/2 a times time squared. And again, only the time gets squared, right? The acceleration does not. And the other equation we've seen up to this point is v final. Again, sometimes you see it v of t, but again, same deal. It's the end of that time period that you're looking at. So v final is equal to v initial plus acceleration times time, right? So those are the equations we've seen. If I want to be consistent in here, I should probably put those dots in there for multiplication. It's the same either way. If I take the dots out, it means the same thing, okay? So if I have this, these are the two equations we have. But they both of them really heavily rely on time, which makes sense. You can't have motion without time. You can't have something move across the screen. If you just look at one frozen point in time, you're going to see this, right? It doesn't move. So you do have to have time. However, what do you do if you don't have a watch that works, or you have a broken watch, or you have something else that's wrong, or just that part's not working out? You don't want to look at the time side of it. What if you want to look at something else? Is there any other way to work these equations for physics? And the answer is yes, there are. Okay, so one other thing I'm going to put on the board, something that's consistent the world round, or close enough for us. For physics, we consider this to be -10 meters per second squared for gravity everywhere on Earth, even though it varies a tiny little bit. We'll get into how that works later on, okay? But gravity's the same everywhere, right? It's the same in Kansas as it is in, Slovakia as it is in Australia, right? They're all the same. If I drop this pen, it'll be pulled down by gravity at 10 meters per second squared, or roughly 9.81, right? Close enough. So if I drop this thing from, say, 2 meters high, and I let it go, when it hits the ground, it should have the same speed no matter whether I'm in Kansas or on the other side of the world, right? No matter where I let it go, from 6 meters above the ground, it should hit the ground just before it hits the ground, that instant before it hits the ground. It should have the exact same velocity. The final velocity for all of them should be the same. So why can't we just figure out the final velocity from the height? Well, it turns out you can. You can absolutely do that. But to do that, you got to get rid of the time factor here. So you have to do something in physics where we love to do this. They do it in math all the time too. But you got to figure out what that variable is, and then you got to take, and once you figure it out and get that t by itself on one side of the equation alone, then you can take and plug back into the other equation. You can substitute back in. Physicists love to do this, okay? And when you do this, you can find really powerful formulas, right? You can find out other ways of solving a problem like we're about to do. So if you are thinking about this on a cliff, and you want to drop a rock, and that cliff is 40 meters tall, how fast is it going to be going at the bottom? And again, it doesn't matter if it's a 40-foot tall cliff in Kansas or in Russia. It should hit the ground at the exact same speed. So what we're going to find out today is how to find that final velocity from nothing but distance, okay? The distance of the fall. Or other terms. You'll see the other terms. As long as we have the formula, we can find any of those terms. First, though, we got to get rid of time, okay? And if I look at this, which equation do I really want to start here to try and solve it for t? This one's going to be a hornet's nest, isn't it? It's going to be a giant mess. But here we've only got time in one place, so I'm going to start easy, okay? I'm going to start with the easy, low-hanging fruit here. I'm going to rearrange this equation. I'm going to solve it for t. So to do that, I'm going to get v final minus v initial, right? And then I'm going to take, and I'm going to have to get that's now times, or equal to a times t. Right? All I did was bump over the v initial. It was added here, so I did the opposite operation there. Okay, now, same thing here. I've got a multiplication factor, so I have to divide this by a. What I do to one side, I have to do to the other side. And so now, my a cancels out, and it leaves me with t. Well, that wasn't so bad, right? That's not too bad at all. Now we've got a variable t. So it turns out that all this stuff is equal to t, so I should be able to take and plug this into that equation in place of t, anytime I have a t. So I'm going to do that now. So first off, I got x final is equal to x initial plus velocity initial times time. Now, I don't want to put t in. I want an equation that doesn't have t. So I'm going to plug this in place of t. So instead of t, this is going to look complicated because it kind of is at first, but it simplifies down really quickly. V final minus V initial over A, that's the same as t. Okay? Now, I also have to put in my acceleration term, so 1/2 times A times t squared. Okay, so now I've got t, velocity final minus velocity initial over A, and I have to square that. Okay? So if I'm squaring this thing, I can actually rewrite that so that A is squared, and then V final minus V initial is squared. And I've got to factor that. No big deal, but I can do it, right? Now I got x's on two places, and I've got all this other complicated stuff in this formula over here, and then x is just hanging out on its own. So I'm going to put it on the other side of the equation just to get it out of the way, okay? I'm going to put x with x. So I have to subtract out x initial here, and what I do to one side, I have to do to the other. So really what I end up doing is subtracting x final minus x initial is equal to all this other business we already had, okay? And this is actually kind of cool because what this represents is our change in our position or our displacement. So interestingly enough, just by moving x to the other side, we get displacement. So maybe we're on the right track or something. That's an interesting result already. But let's keep going. All right, so we've got this. Let's factor this one first, it'll be easier. Okay, this is actually v over 1 times that fraction, right? So that means bottom times bottom. So on the end, let me rewrite this down here. Exact same equation, but now I'm going to work out this part of it. So bottom times bottom means I'm going to have A on the bottom. And on the top, I'm going to have VI times each one of these things. So I end up with VI times VF, and then minus VI times VI minus VI squared. Okay, so that term is now the same as that one. That one's done. You can check it off our list. All right, so we got 1/2 times A times all this business. Okay, so let's look at this. V final minus V initial squared. And look at this, I have an A squared on the bottom, don't I? So this A is really A over 1, okay? So if that's the case, I have an A on the top and I have A squared on the bottom. I can get rid of one of my A's. So this will take care of this squared, and this will take care of that entire term. So that's starting to look a little prettier now, right? It's not quite so ugly and hairy. And I'm also going to do one other thing. I'm going to expand this, okay? So instead of VF minus VI squared, I'm going to write VF minus VI again, and we have to multiply it out, all right? So our next step, let me write it down here. Again, I'm going to copy over what I have so far. X final minus X initial, or my displacement, my delta X, is equal to VI times VF minus VI squared over A, that's that piece, plus, okay, now I've got 1/2, right? And here, so here I've got to figure this out. So I've got VF times VF, so I get VF squared, and then I get VF times minus VI, so I get minus VF VI, and again I go minus VI times VF, so I get another minus VI VF, or VF VI, same thing, right? You can multiply it either way. And let me simplify that down too. Okay, I have two of them here, so I'm going to put minus, instead of having it on the board twice, I'm going to put minus 2 VF VI. Okay, just to simplify it in the middle of the problem. And at the end, I get minus VI times minus VI, so I will get a minus times a minus will give me a plus, so I get VI squared plus. Okay, now all of that is simply over acceleration, and that whole thing is times 1/2. Okay, so we have A on the bottom, we have A on the bottom, don't we? Let's go ahead and make this easier to look at. Let's go ahead and get rid of our A. If I multiply this whole side by A, right, that A cancels out, and so does that one. But what I do to one side, I have to do to the other. I multiply the whole thing by A, so now I've got to multiply this side by A. All right, so I'll get A times X final minus X initial, okay? And let me make it easier to look at over here again. So let's get rid of all the A's on the bottom. Those went away. So now here's the equation we're looking at. Okay, we have VI, VF, and over here we have minus 2VF, VI. Well, that's the same term, isn't it? So really, I have this one goes away because if I add a plus to that 2 minus, I end up with just a minus VF, VI. But wait a minute, I shouldn't have done that yet. I have a 1/2 in here I didn't figure out yet. Sorry, guys. Back that up. Okay, so I got a 1/2 times all of this, so I got a 1/2 VF squared, and I got a 1/2 times a 2, so I just have VF, VI. And then I also have over here a 1/2 times my VI squared. Okay? So we've simplified it down a little bit more. I distributed that 1/2 throughout. Now let's look at what we have. Okay, VF, VI, it's minus here and it's plus here. I have 1 plus and a 1 minus. Those entirely go away. Cancel out, don't they? Now over here I have 1/2 VI squared, and over here I have VI squared. So I end up with, and this is a minus and this is a plus, so I end up with minus 1/2 VI squared when you add those two together. And okay, so now I've got a pretty simple side over here. I've got minus 1/2 VI squared plus 1/2 VF squared is equal to all this. I got a half in both of these things, don't I? Can we get rid of that now? Again, you want to get rid of a 2 on the bottom, you multiply by a 2 on the top. 2 over 1 is just 2. So if I multiply by a 2, I get rid of that, I get rid of that, I get rid of that. But what I do to one side, multiply by 2, I have to do to the other. So I get 2 times A times our displacement, or our change in our x. Okay, and let me make this easier to look at. Okay, now I have a minus VI. Again, it's a minus, so maybe I should put it on the other side to make it a little cleaner. So I'm going to do that. Okay, I'm going to take and put plus VI squared. Okay, so VI squared plus 2A, change in my x. And all of that is now just equal to whatever's left over here, which is VF squared. And guys, that right there, that's your timeless equation. So now we're done. If you know the change in the distance, how far it's going to fall, right? Is it going to fall 40 meters? Well, that's 40 meters minus 0 if you're going to the ground. So your delta x, your change in x will be 40 meters, so you just plug that in. Acceleration due to gravity, that's always negative 10, okay? So you get negative 20 times 40. I'll plug this in a second, right? And then you get your initial velocity and your final velocity. So again, it accounts for all these things. You could find your final velocity. If you wanted to find your change in x, you could. If you wanted to find your acceleration, if you didn't know that, you're on another planet, it still works. If you need to know your initial velocity, you can do that too, okay? But I'm going to get rid of all this stuff so I can look at it a little better, okay? And I'm going to rewrite it up here. So let me get my eraser rather than my fingers, right? Okay, so that's kind of cool, guys. We came up with an entirely new formula just by substituting for t into the original equations we already had. We came up with a new equation, and no longer do we have to have time. We can work it out without it, right? So let me make this look a little prettier. VF squared is equal to VI squared plus 2 times A times x final minus x initial. And I'm going to write it a second way. VF squared is equal to VI squared plus 2 times A times your change in x, right? I could put delta x, or I could put displacement here. Sometimes they call it D for displacement, all right? But I'll just put delta x for right now. Now realize this could work very well in our y direction as well as our x direction. Anytime you want to use this for the vertical instead of the horizontal, same thing applies. You just have to switch out x for a y, okay? And the way I'm going to use it is actually a y. I'm going to be talking about gravity and how it falls with gravity. So there is our nice, neat, clean equation, and this is probably the simpler version of it, but just so you have it both ways, okay? Now I told you, we had a rock starting at 40 meters high. It's going to hit the ground, which is, I'm going to call 0 meters. Again, anytime they don't tell you otherwise, if they tell you a height and it's referenced off the ground and it's going to hit the ground, know that the ground's got to be 0. If they don't tell you initial or final position, one or the other you could always set to 0. Anytime you like to, you can always throw a 0 in there, okay? So I know my rock is 40 meters up on a cliff. I'm going to drop it. It's going to go and hit the ground eventually. Okay. I know acceleration due to gravity is negative 10 meters per second squared. And again, I've got this times 2. Okay, there's my 2, my A, and my delta x, or my x final minus my x initial. And my initial velocity, this is another interesting thing. If I'm dropping it, that means I'm just holding on to it. I have no initial velocity. So this is 0 meters per second squared. But again, it'll go away. We'll do that later. And we wanted to find out how fast it's going in the end, right? So I got v final squared. We're going to have to take care of that squared, but that's okay. It's not a big deal. So let me rewrite it. V final squared is equal to, I'm getting rid of that because I don't care about the 0 anymore, is equal to negative 20 meters per second squared, 2 times my negative 10, times 40, difference between those two. So if I multiply those out, I'll get 2 times that, I'll get 800, right? 40 times 20, right? You got to carry both the zeros through, and then 2 times 4 gives me the 8. So I get a v final squared is equal to negative 800 meters per second. Now, here's what I want you to do. If you've got a negative in here, and a lot of times you will, actually I was probably just not careful, and somehow if I switched my final and my initial, if I did 0 and negative 40, then all of a sudden it works out, and I would actually get a positive here. No big deal. Either way is fine. If you get a negative, though, just ignore it. Ignore it and then come back to it later, okay? So you can just pop that negative out, okay, do your equation, then pop the negative back in afterwards. Either one's okay. Technically, you should be doing it this way, but, you know, whatever, it's fine. I didn't put my initial. My initial was like height, right? My height was 40. My final was 0. I put it in backwards. That's why it came out positive. Or, sorry, it came out negative. Now it's positive now that I fixed it. So on my v final, not my v final squared, so I have to take the square root of that guy. What I do to one side, I have to do to the other. So my final velocity is going to be square root of 800, and I had this multiplied, so it actually should have been meters squared over second squared. Square root of 800 meters squared over seconds squared. And when I take the square root of this, I'll find my number. Great. I'll take the square root of meters squared and square root of seconds squared, so I'll end up with the square root of 800, whatever that number is, meters per second. And that's a velocity, right? That is totally a velocity. When it hits the ground, it is going to be going fast, all right? So, in fact, if I work that out, why not? I'm already here. You guys are already here. Let's go ahead and take a look and get the satisfying number. You guys always like that satisfying number. So instead of leaving it in square root format, of course, now it's going to take forever to open, right? But here we go. All right, so square root of 800, I get 28.2. 28 point, basically 3 meters per second. That's my final velocity. Doesn't matter if I drop it in Kansas, Colorado, or, you know, Eastern Europe somewhere. Doesn't matter at all. I'm going to end up with that exact same velocity no matter what I do because it's falling from the same height and falling downwards. So there's your timeless equation, okay? So remember this one. I don't care which of these formats you use, but those are your timeless equations. They're on your Unit 1 equation sheet. Don't forget that you have them. You can plug them in and use them just like anything else. Anything that falls, anything that moves, can still, as long as it has a consistent acceleration and you know all the other terms, you can still find out how fast it's going to be going or how much different distance it covered if you know all the other terms, even without time. Okay? That's it.